I welcome you all in this NPTEL online certification course on mechatronics. Today we are going to talk about op-amp as a signal conditioner. In the last slide, last lecture, I discussed with you the op-amp, its assumptions in the modeling of the op-amp we have seen, and we have seen the use of or how can we use the op-amp to amplify a signal with the help of external elements or external resistors rather. Today in this lecture we will talk about how can we manipulate a signal. Manipulation, I mean that how can we add the signal, how can we subtract the signal, how can we integrate the signal, how can we differentiate the signal. So, all these and the various other uses of operational amplifier as a signal conditioning unit we are going to discuss today. I hope you will enjoy this lecture. So, here we are at this place right now, input signal conditioning and interfacing. First of all, let us look at the adder circuit. Okay, that is, I have got two signals and I want to add those signals. Okay. So, here what we do, the non-inverting side we ground it. In the inverting side we have the two signals V1 and V2 over here, and these are the input side resistances R1 and R2, and you have the feedback resistance over here. Okay. So, a portion of the output is fed back to the inverting side over here. Now, to see its use at op-amp as the adder of the two signals, let us analyze it. So, for that purpose I have drawn the equivalent circuit of an adder. Okay. So, these are V1, V2, R1, R2, this is current say through this one I1, I2, and this is output current from over here, and say this is what we are shorting as per the assumptions for the op-amp. Okay. So, now at C we see that if I apply the Kirchhoff current law, I have these three currents coming over here. So, I can just them sum it to the 0, and then I can substitute I1 is simply V1 by R1, I2 is V2 by R2, and I out is V out by RF is equal to 0. So, from here I can just write V out is equal to minus of RF by R1 V1 plus RF by R2 V2 over here. Now, if I take this R1 and R2, they are to be equal to same R. Okay, R1 and R2 as say same equal to RF. Okay. Then if I put it over here, then you can just see that what I get is minus of V1 plus V2. So, sorry. So, I am able to sum up these two signals, and although I am getting this signal inverted, so I can use another op-amp to correct this inversion. Okay. But I am able to get the summation of the two signal over here. Now, let us look at use of op-amp for the subtraction of the two signal. Okay. So, for the subtraction of the two signal in the previous circuit we make some modification over here. Okay. So, at the non-inverting terminal I supply the another signal V2 over here, and there is another resistance of the value RF which is being used over here. So, in this configuration I can use for the subtracting purpose, that is I will be getting V1 minus V2 from this one. Let us see how this is done. So, again I have put up the equivalent circuit for that, okay. And so this portion actually I can analyze by over here, as you can see. You have R1, you have RF, this is the point C over here, okay, and this is the V2 over here. I will come back to it little later, okay. So, the voltage at C here Vc, as you can see, this is basically V2 minus IR1 basically, okay, because it is V2 minus Vc, this is basically what I into R1. So, you have Vc is equal to V2 minus I R1 over here, okay. So, from here you see that Vc is equal to V2 minus I can write as V2 by R1 by RF, R1 plus RF into R1. How can I write this I is equal to this one? Basically you can see this equivalent circuit over here. If there is a current I from here, then your V2 is equal to basically I into R1 plus RF, okay. So, I is actually V2 by R1 plus RF. So, I have just substituted that I is equal to V2 by R1 plus RF into R1. So, that is there. So, from here this is there. Moreover, this Vc or if I simplify this, then what is this V2? Vc is equal to V2, you have R1 plus RF minus R1. So, R1 gets cancelled. So, you have RF upon R1 plus RF, okay. So, I have this equation, the voltage at C. Also as we have been seeing, I1 plus I out over here, this is going to be 0. So, I1 is equal to minus I out. Now, I substitute for I1 basically, that is V1 minus Vc by R1, and I out as V out minus Vc by RF with a minus sign. So, this is our equation. So, from here I can find out V out, okay. V out I can find out RF by R1, V1 plus Vc over here. So, this I out is minus RF by R1 V1. I just simplify this, and the Vc I have already calculated in the previous slide over here, here this one. So, I substitute it over here. So, I get this one. So, if I substitute this Vc over here, this is what I am going to get. So, here you can see that what I am having is, I am having the difference of these two signals V2 minus V1, and this RF and R1 will basically decide how much I am going to amplify it. Next, let us see the use of operational amplifier as an integrator. So, for that purpose, in the feedback circuit, if I replace the feedback resistor with a capacitor of say capacitance Cf, okay, here, and I have a signal say V1 supplied to the inverting side, and the non-inverting side is grounded over here, okay. So, the voltage across capacitor is actually Q by C. This is the general equation which we all know, okay. So, from this one I can write about V out, if I differentiate this, then V out by dt is basically going to be 1 by Cf dq by dt. Okay. So, V out by dt is 1 by Cf dq by dt, or this one dq by dt, you know, this is basically I out. So, I replace with I out, and this is what I have. So, from here I have the V out is equal to integration of I out, I use a dummy variable tau over here, integrate it from 0 to t, and 1 by Cf is there, okay. And you see I1 plus I out is equal to 0, again from the assumption for the op amp. So, I out is minus of I1, okay, and this I1 is actually from here V1 by R1. So, what I get basically here is V out is equal to this one minus 1 by CF R1 V1 dt, because this I out is minus what I1, and this minus I1 will be basically minus V1 by R1. Okay. So, this is what I get, and here you see what we have got is that my input signal that is which was V1 over here, that has been integrated, okay, and this is what I am getting output. Okay. So, this way I can use the op-amp as an integrator. Next, let us see the op-amp as a differentiator. Okay. So, we can get the differentiator circuit if we replace the input resistor of the inverting op-amp circuit by a capacitor as seen in this figure. Rest of the things are same, that is you have a feedback path here with the feedback resistance RF, and this non-inverting side is grounded. So, if I look at the equivalent circuit over here, say this I1 is the current at the input side, I out is the current at the output side. Okay. So, dV1 by dt basically can be written as I1 by C1. Okay. So, we can write this one, and we see I1 is equal to minus I out. We already know from our earlier assumption for the op-amp. So, my I out is basically V out by RF, which we can derive from over here. So, V out is minus RF I1, I can write after substituting for this one. So, my V out is equal to RF minus RF, and I1 I can replace this from here. Okay. So, that is C1 dV1 by dt. So, here you can see that what we are getting is basically my this input signal is getting differentiated, and it is multiplied by some factor with a inverting sign over here, and that I am getting the output. Okay. So, this is what this is how we get the differentiated signal. Then coming to the other uses of the op-amps, these are used very popularly for the as a sample and hold devices, and sampling and holding is basically required when we are talking about the conversion of analog signal to the digital signal. Okay. So, in this when we are talking about conversion from analog to digital, okay, signal value must be established while it is converted to the digital representation. Okay. So, here what is done is that here this is output is connected to the inverting side over here, and there is a switch which is used, and there is a capacitor with capacitance CH that basically which is used for holding of the holding purpose, and this is your input side. Okay. So, when this switch is closed, when this switch is closed, basically that time it is used as a buffer. Okay. So, whatever output you are getting, that is going to be the same as the input. So, V out is equal to V2. Okay. And when the switch is open, this switch is opened over here, then the capacitor, this CH actually holds the input voltage corresponding to what? Last sampled value, since negligible current is drawn by the follower. Okay. So, the relationship will be what? This V2 at the t sample time, this is going to be there, V out, that is t minus t sampled. Okay. So, this is what is going to be there, where t sampled is the time when the switch was last opened. and this sample and hold amplifier are used to hold an instantaneous value of the analog voltage until an AD converter is ready to convert the signal. Next, the purpose of or good use of the op-amp is as a comparator. Okay. As the name indicates, the comparator basically compares the two voltage signal. Okay. It shows which of the two signal is larger. Okay. So, for that purpose what we do is that we in the inverting terminal we send one signal, say V1, and in the non-inverting terminal we send another signal of voltage, say V2. Okay. So, there is no feedback. Op-amp with no feedback can be used as a comparator. Okay. That is it is in the open loop configuration, since we are not going to have any feedback. Okay. Now one of the voltage is applied to the inverting input and the other is applied to the non-inverting, as I explained. Now, here there are three things possible. If V1 is equal to V2 sorry, if V1 is equal to V2, there is no signal. Okay, that is no output is over there. Okay, so you are basically at this place. Okay, here I have plotted input versus the output, and if V1 is greater than V2, okay, then output jumps to say a minus 10 volt range over here. Okay, there is saturation over here. So, this comes to the minus 10 volt. Alright, and if V2 is greater than V1, it jumps over here, other side, okay, jumps to plus 10 volt. So, comparators can be used to determine when a voltage exceeds a certain level, that is the output then being used to this output then can be used to initiate some action in your subsequent circuit. One of the very beautiful application of the of this is in the CD player, to check the focus of the laser light on the CD. Okay, so you have the op-amp over here, there are two terminals V1, V2, and this is your output side. Okay, so these terminals are connected to the photodiodes over here. Okay, these photodiodes are there, and this one say this V1 side, this inverting side is connected to this one and this one, whereas the non-inverting side is connected to this diagonally this one. Okay, this one, and here say they are connected to this one. Alright. Now, when there is a laser beam in perfect focus, there is same voltage, okay, same voltage. So, V1 is equal to V2, you get it from here. Alright. So, you do not have any signal. Okay. And when there is out of focus, either this way or it is this way, you have a certain signal. Okay. So, if you have the beam out of focus, then you have a signal. So, this is the application where the comparator is used. Now, let us look at the filters basically. Okay. Filters are also important device in a mechatronic system for the signal conditioning purposes. Okay. It is as the name indicates, it is a process of removing a certain band of frequencies from a signal and permitting other to be transmitted. Okay. And these filters could be either active or passive. Passive, as the name indicates, a filter made up of using resistor, capacitor, inductor, and there is no power source over here. Whereas, the active filters are those which involves operational amplifier, and you know that the operational amplifier need power supply for them to work. okay, that is why they are called active filters. Okay. So, here you have the example for the passive filter. You have a resistor capacitor over here, this is your input side, this is your output side, and here you have the active filter where an op-amp is there. Okay. You have resistor capacitor and all. So, let us look at the definition of these filters basically. Okay. Low pass filters. Okay. Low pass filter, as the name indicates, they allow the lower frequencies and they block the higher frequencies. Okay. So, this signal transmitted and frequency if I am plotting, only this range is actually the allowed one, okay, and other higher ranges are blocked. Okay. And high pass filter, only the higher signal of a frequency higher than a particular frequency, they are allowed, okay, and others are blocked. Then you have a band pass filter where we allow a frequency of a particular band to be passed through. Okay, that is it blocks all frequency except those within this range. Okay, and band stop filter blocks only the frequencies within a certain range, allowing all other to pass through. So, here this is the pass band, this is the pass band, burst frequency of this range is going to be blocked. So, this is what is the band stop filter. So, the low pass passive filter is this one where you have resistor and capacitor with used in this fashion, and high pass passive filter is this one with capacitor and resistor being used in this fashion. Then let us look at what are the parameters specified in op-amp data sheet. What are the manufacturer, what all parameters the manufacturer specifies in the data sheet for the op-amp. Okay. So, these parameters could be input parameter, output parameter, dynamic parameter, we will look at this. So, the input parameter first of all is the input voltage. Okay. So, it is the maximum input voltage that can be applied between either input and the ground. Okay. So, we have the two input ports, inverting and non-inverting. So, between either of that and the ground, how much maximum input voltage we can supply. Then the input offset voltage, okay, the voltage that must be applied to one of the input terminal with the other input being at 0 volt to give a 0 output voltage. Okay. So, as I explained in my last lecture about the offset. Okay. So, this is how it is defined. Then input bias current, the average of the current flowing into the both the input when the output voltage is 0. This is what we call it as the input bias current. Then input offset current, it is the difference between the input current when the output voltage is 0. Then input voltage range, this is the range of allowable common mode input voltage where the same voltage is placed in the both the input. Then input resistance, it is the resistance looking into either the input with the other input being grounded. Now, what are the output parameters? These are the output resistance, output circuit current, output voltage swing. What is the output resistance? It is the internal resistance of the op-amp output circuit. And what is the output short circuit current? It is the maximum output current that the op-amp can deliver to a load. And what is the output voltage swing? It is the maximum peak to peak output voltage that the output can supply without saturating or the clipping. Then what are the dynamic parameter? So, dynamic parameters are open loop voltage gain. Okay. So, it is the ratio of the output to the differential input voltage of the op amp without external feedback. As the name indicates, it is a open loop voltage gain. Then what is the large signal voltage gain? It is the ratio of the maximum voltage swing to the change in the input voltage required to drive the output from 0 to a specific voltage. Then what is the slew rate? I talked about slew rate in my previous lecture also. It is the time rate of change of the output voltage assuming a step input, okay, with op amp circuit having a voltage gain of 1. Then what are the other parameters? There are certain other parameters which are also specified. Maximum supply voltage, it is the maximum positive and negative voltage permitted to power the op amp. Then what is the supply current? It is the current that the op amp draws from the power supply. Then common mode rejection ratio, it is the ratio of the difference mode gain, okay, that is the output gain corresponding to the difference between the input, to the common mode gain, that is the output gain when the same voltage is applied to both the inputs, and this is usually expressed in terms of decibels. Then the channel separation. See, when there is more than one op amp in a single package, a certain amount of crosstalk is present, okay, and what do you mean by this crosstalk? Okay, that is the signal applied to the input of one op amp producing a finite amount of signal to the second op amp, even though there is no direct connection between both the op amps. Okay. So, this is specified by the channel separation. Okay. So, these are the further references which I have used in preparing these lectures. So, if you want to read it more, please go through these references. Thank you very much.